Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, those few of us who can manage to get up at 10:30 and those of us who will watch this on tape are thrilled to have Xiaotie Deng here. Tsinghua is a frequent visitor, one of our very favorite visitors, and he will be talking about game and market equilibria, approximation, and smoothed complexity. Good, I was about to call you too.
So, okay, so basically in this talk, I would like to present some of our recent work in computational game theory. In particularly, I would like to focus upon the computation and approximation of game and market equilibria. So I will focus not only on the traditional worst-case complexity of these game theoretical problems, but also study the so-called stability of the hard instance in the framework of smooth analysis. So, this is a joint work, mostly with Xi Chen, who is currently at Princeton, and Xiaotie Deng from Hong Kong. And also some of the part of work is joined with Li-Sha Huang from Tsinghua. He's now currently in Google China, and Paul Valiant, who is still a student at MIT. So I know there's a lot of game expert in game theory here, but let me start basic anyway to set up the framework. So to understand game theory, I think the easiest place to start is something we are more familiar with, that is optimization. And I will quickly introduce some of the basic terms, and then give you time to adapt to my accent, and then we can talk about the real work. So what is optimization? So in optimization, we often confronted with a problem that is, in the simplest case, we have single objective functions that is whose value is dependent upon multiple decision parameters. Okay, so the parameters may subject to certain constraints, either individually or globally, subject to certain constraints. For example, linear programming is a special case that all its decision parameters has to stay in a convex set. Then you want to optimize. And so then basically we would like to, for example, in the simplest case is to just optimize a single objective function. Okay? And so there's a lot of so-called solution concept surrounding with this problem, which we are familiar with. And if you're a smart president, most likely you will go for so-called global optimal for the objective function of the country. And if you're not that smart president, like our current one, so you may go for hopefully even a local optimal, depending upon the neighborhood structures.
I think our current president got a sign wrong, but anyway.
Maybe even get a sign wrong sometimes. But that's still an optimization problem. It's still optimization problem.
Yes.
And if you're a practical president, most likely you will go for some approximation notion of those, right? So those are the solutions in the so-called feasible domain that either approximately or locally or globally approximate an objective function. Okay. So naturally, the world is not this simple. Very often we actually have multiple objectives. Namely, it's not just single objective optimization, right? So in the multiple objective optimization, we may have many, many different objective functions. For example, each state has their own utility function they would like to optimize. And still, we are not in a game setting yet, because in the traditional multi-objective optimization, we still have a single person in charge of all decision parameters. Right? So a single person is still in charge of all decision parameters. However, it needs to make a trade-off between different objectives. Right? Because what is good for country may not be good for Washington state. And so there must be certain trade-off has to be made. And hence there's different notion of solution concept are proposed and developed and matured in those domain too. For example, Pareto optimum, namely certain trade-off among the solution, and or its approximation has been studied in those domain. And the game setting basically is one more step, slightly different from so-called multi-objective optimization. So in the game setting, again, we do have multiple objectives. But instead of a single person control all the decision parameters, we have different individuals control the different fraction of the decision parameters. And they have their own individual objectives. Right? For example, the governor of California or governor of Massachusetts or the president, they all would like to maximize their own utilities. But they can only control their own parameters. For example, the president can only control ex-USA, and the governor of Illinois control somewhere, hide it here, ex-Illinois, and so on. So this actually presents further difficulty in terms of problem formulation as well as solutions. Right? So the difference comes from is this individual control of the decision parameters, and also the globally is a trade-off between objective functions. Right? So this essentially gives us a setting of the games. And so along this line, this different notion of solution concept has been proposed. And in this talk, I will focus upon a simpler one, namely Nash equilibrium. Okay. So Nash equilibrium is mostly built upon a notion called best response. The best response can be at high level defined as following. So imagine that the governor of California is the last to decide. And imagine that everybody else already choose their decision parameters. Then the governor of California, clearly for selfish purpose, try to promote the interest of the state, will choose its own decision parameter to optimize this particular objective function. Because it's not his concern to worry about Illinois or Massachusetts. It's really try to optimize this. So the choice of CA when everything else is fixed is so-called the best response of the governor of California based upon its own objective functions. Right? So naturally you can define so-called best response of every player or agent in the system. Right? So this often introduce either computation or dynamics. Right? Because everybody probably hopefully wants to be the last one to move. Right. So if you continue to do this, I update, you update, this will give you a dynamics. Right? It will go from a solution basically essentially move around the configuration of solution space in a particular style of working. And Nash equilibrium essentially is the fixed point of such a transition. Namely, it's a setting of the decision parameters. And nobody actually is willing to move, assuming that the rest stay the same. Right? So basically, it doesn't matter who you call upon to say, okay, it's your response time now, and they will still choose the current configuration. Right? Because by moving to other configuration, can only do worse or equal. Right? So those are the definition called equilibrium points. Okay? So that's basically the concept which we are going to discuss in the talk. So as you can see that game theory is computational game theory is a highly interdisciplinary field that intersects, optimization, possible economics, game theory, theoretical computer science, and a variety of applications. And therefore, there are sort of multiple ways to enter a discussion of this subject. So in this talk, I would like to choose a particular entrance that essentially led us to our main result. Okay, so it's a very specialized entrance. I don't claim this is the standard entrance. Okay, so a few years ago, in a joint work with Dan Spielman of MIT at that time, so we proved the following results about linear programming. That is, if you give me any linear program, and if you consider a particular simplex method, then we're able to show that suppose the linear program you received is a slight perturbation of any linear program given by the adversary. So then we are able to prove that even though in the worst case, that particular version of simplex algorithm runs in exponential time in the worst case, but subject to the fact that your input is slightly perturbed when it's given to you. So this perturbation can come from, in practice you did measurements, and what given to you is basically the result of measurements, and hence it's slightly imprecise, right? So you receive data from this sort of slightly imprecise model. Then we are able to show that that version of simplex method actually runs in expected polynomial time in input size as well as 1 over the magnitude of perturbation. So clearly, if you don't perturb, it's a worst case analysis, right? Basically, you're doomed to go with exponential time. But once you have certain degree of perturbation, for example, in the precision of polynomial magnitude, then the simplex method will run mostly in polynomial time in every neighborhood, right? Independent of where you centered the original one. So we call this smooth analysis. Essentially, in the smooth analysis, we study the complexity of a problem or an algorithm, assuming that your input are subject to a slightly perturbation. And we measure the complexity as a worst case, subject to this model. Okay, so that's the smooth analysis framework. And shortly after we finished this work, and naturally we began to give a talk, we had a visitor to Boston, and a gentleman by the name of John Rife. So for those who know him or didn't know him, John is a very interesting person, and one of his characters is he always asks questions. I mean, if you in your conversation with him, basically he just continues to ask you questions, and some of those are brilliant questions. So in our meeting, he asked the following. He said, "Well, now you show one classical algorithm, namely simplex, has polynomial smooth complexity. So what about the smooth complexity of another classical algorithm, which is almost like simplex algorithm, called Lemke-Hausen for two-player games?" Okay, so it's a fairly natural question, because it's when the simplex method essentially is a walk along the exterior of a single polytope. The Lemke-Hausen algorithm essentially is a walk on the Cartesian product of two polytopes. So essentially, he said, if you walk on one polytope with short walk, what about the Cartesian product of two in this particular fashion? So, of course, the first time he asked, my quick response, that's a very good question. It's nice. I will think about it. We'll think about it. So then we began to give a talk on smooth analysis. It turned out that this became one of the most popularly asked questions during my talk, and probably during Spielman's talk too. Actually, one of the two most popularly asked questions. And people continue to ask very similar questions to this nature. Okay, the first time you say it's a good question. Second time you will say that's a great question. Third time you say excellent question. Once you run out of way to describe the questions, you say, well, maybe I need to solve the question, at least give a try, right? So that's how I got hooked into this particular problem. So what is a two-player game? Two-player game is a very special case compared with the one which I described earlier on, which is multiplayer games. So in two-player game, you only have two players. Each has a set of choices for the decision parameters. So it's sort of in a standard matrix form. The first player, let's call it role player, has few choices depending on how many rows you have, and the second player, for example, choose columns, and those games can be fully described in full information sense as a 2x2 matrix. basically at every intersection, you will receive the payoff depending upon your choice. Right? So for example, the first player chooses the second row, second player chooses the first column, they will mutually receive such payoff. Right? So these two matrices clearly describe the situation. So that's why sometimes we call it bimatrix game. It's a game defined by two matrices. And here is basically one of the special game invented in my native country, China, called paper, scissors, rock, right, in the world. And this is, for example, the payoff. Right. And so this game actually is interesting in the following sense, that there's no so-called pure equilibrium strategy. So for example, it doesn't matter who chooses what, and one of the person is also willing to move if you give the person chance to respond. Okay? So that's why in this game, actually, the equilibrium points only exist when you go to so-called mixed strategy. You randomize. Right? So I actually did this game with my nephew when I went to China when he was 4. And at the beginning, he played definitely deterministically. So after a few iterations, I can just continue to beat him. But you can see after a few days, he randomized. Right? So for example, one of the particular solutions is a third for this particular game. Okay. So mathematically, here is the description that suppose I have two matrices A and B, and a set of probability, X star and Y star, form a so-called mixed equilibrium if the following is true. That is, if the second player stays the same, the first player changes to a different probability distribution. It can only lose, cannot gain. And simultaneously, the other condition holds. So that's why it's simultaneously best response to each other's setting. Okay? And of course, in practice, sometimes we may go for a little bit of approximation, depending upon your machine precision, or just depending upon the amount of time you may have. So for example, one popular notion of approximate equilibrium is what we call epsilon approximate Nash equilibrium, which can be described as X star Y star is epsilon approximate Nash equilibrium if when you change your mind, you don't gain more than epsilon in additive way. So for example, epsilon is a quarter. It just means that you can switch, but you never gain more than a quarter. Okay. And so mathematically, it's all set based upon Nash's famous theorem. Basically, he proved that doesn't matter what A and B are, at least solution always exists.
Do you have additive epsilon or?
Additive, yeah.
So do you have magnitude restriction on it? Because
yeah, so the result extends to the this is a weaker notion. So depending on which direction you want to prove.
I think this is a stronger notion.
Yeah, depending on which direction you want to prove.
Yeah.
Yeah. So depending on which direction you want to prove. So for my result, this is stated to be the one which can be implied to the other one. Yeah. And so Nash proved that such thing always exists. Right. So that's why as decision problems, it clearly we will not be NP complete. You just simply say yes. Right? Do you have a solution? You said yes. Right. So the main thing we are going to consider is search problem, namely the input are A and B, potentially epsilon. You would like to return a pair of solutions. Okay. So that's the search problem that we are going to consider. So of course, as I started earlier, there's multiplayer games. For example, 3-player games, 4-player games, or the 51-player game, which I started at the beginning. But in the talk, I will mostly focus on 2. The result can be extended to other number of player games. Okay. So what is the complexity of this problem? So there's a special case which has been considered long before Nash got into the space. So this is called zero-sum 2-player games. So when A and B add up equal to 0, or any constant, so namely one player's gain is equal to the other player's loss. So in such case, back in 1928-ish, von Neumann actually considered this game, and he observed that mixed equilibrium exists at that time, and also there's a sort of his famous minimax theorem. and eventually can be captured as so-called the duality of linear programming. Okay, and but still back then, it's all he did is basically say the existence of the equilibrium, and in fact, his proof went through. Original proof didn't go through duality; it went through the standard Brouwer's fixed point. So essentially, very similar to Nash's proof for the general case. So von Neumann actually went through a sort of complicated proof for a much bigger theorem, which he stated a special case. Okay. And so it's only take 50 years for this duality to be realized algorithmically, right? 50 years later, when Kachin observed that the ellipsoid algorithm can solve a linear program in polynomial time, then this basically said that the two-player games can be solved in polynomial time, assuming a plus b equal to 0. Okay, so for example, the result I mentioned about the smooth complexity of a simplex method can also be twisted to show that if the game A is slightly perturbed, then the simplex algorithm also finds equilibrium in polynomial time. Okay, so this basically is the context of John Rife's question. That is, in 60s, one of the most popular methods for finding equilibrium in two-player game is so-called Lemke-Hausen. So Lemke-Hausen, I think started from Lemke, extended certain style of the simplex algorithm to basically handle these two polytopes. And he's able to show this style parameterized simplex-ish algorithm eventually can lead to an equilibrium in general two-player games, right? So if history is any guide, those are basically the possible conjectures. If you just look at this side, possibly you will ask the following question. For example, Crystal Papadimitriou asked, is the two-player game in P? Right, so that's one of the first time I think it's more explicitly brought to the attention of theoretical computer science. Is in this conjecture, is by matrix game in P. And for me, basically, to enter the space, I'm mostly aiming at a much less ambitious question, is by matrix game in smooth P. So that's essentially where I started. Namely, I would like to show that it can be solved in N and 1 over the perturbation. Okay. And so John Rife's question is much more concrete. He's asking, does Lemke-Hausen has a polynomial smooth complexity? Right, so that's the context. Okay. So let me say one word. That is the reason I put the past following, because the simplex algorithm and the interior point, or even ellipsoid, can all be viewed as some kind of past following algorithm. You find a solution, you find another solution, you follow a path. For example, the simplex algorithm follow a path on the exterior of the polytope, and some version of interior point algorithm follow a path in the interior of the polytope. Right. So this basically follow a path on the sort of the Cartesian product of two polytopes. Okay. So let me just be a little bit one step concrete about the smooth model, which I'm considering in this talk particularly. That is, if I have a two-player game, suppose someone gave me a two-player game, ultimately the one I will receive is a slightly entry-wise perturbation by magnitude no more than epsilon. Okay. So that's the model which we will consider. This is what you receive, you want to solve. You don't care about the other one. You don't see the other one. You receive this one. And there's a very interesting simple connection. This is just take one line to argue. That is, if you look at the Nash equilibrium of the perturbed game, because the objective function for each player is a bilinear function, it's very easy to argue that actually every equilibrium of a perturbed game is a 2 times epsilon approximate Nash equilibrium of the original one. So imagine that this problem has a smooth polynomial time algorithm. This actually means that the original problem will have a fully polynomial approximation scheme, randomized. Right? You can just perturb yourself. If you want to solve the equilibrium, perturb yourself. Imagine you can solve it in a smooth model. You solve it and you go back, right? So clearly, this is one of the places the smooth complexity and the approximation complexity are approximately equal. So this is the second most commonly asked question when we give a talk on smooth analysis. People ask, what's the connection between the smooth complexity and the approximation complexity? And in this particular case, they are essentially the same. Okay, so we are going to use this bridge.
Well, are they the same? You can go the other way around too. Or if you can solve it, then you don't
They're connected.
need to smooth.
They're connected, yeah. I said that essentially, right, but not right. So therefore, a unified question, which draws my attention, is does two-player game has a fully polynomial approximation scheme, right? So there's two possible versions depending on who you are. If you, theoretical computer scientists, the most commonly used version is this. Can you compute an epsilon approximate Nash equilibria in polynomial time in n and 1 over epsilon? So that's one of the version. And if you're a numerical analyst, probably you don't care about this question. You mostly care about this question. That is, can you get the first log n bits of your equilibrium? So this is normally what we call single or double precisions, right? Because our word length is roughly the log of our problem size, right? So can you get the few log bits out? Okay. So here is the main result which I'm going to present. That is, unfortunately, we're able to show that it's unlikely that there's a polynomial time approximation scheme for this problem.
Fully polynomial or polynomial?
Fully polynomial, yeah.
It's still possible with
It's still possible with a polynomial with 1 over epsilon on the exponent. That's still a possibility. And so it's hard to get log n bits. It's hard to get log n bits. And so this is actually very interesting in the following way. That is, if you look at local search, which is another solution space for optimization, for most of a local search problem, to find an approximate solution, you can do it in fully polynomial time. However, for the two-player games, the approximation complexity is same as exact complexity if you're looking for fully polynomial approximation. If you can solve in fully polynomial time approximation, you can just solve original problem exactly. But in the local search, those two things are different. So it really reveals some mathematical discrepancy between, for example, the standard optimization and equilibrium computation.
So why did you not have the same thing in the smooth analysis? You would also think there, if you have an epsilon.
Right. So this will imply that. So it's actually.
Analysis of the origin of the linear program, you would have the same thing too, right? That you can all.
The approximation one. Yeah, it depends on how you set up your objective functions. Yeah. So you have depend on
just for the simplex.
Right. Depend on the condition number of the program. So because here it basically just by objective is a real condition. That's why you have this straightforward 2 epsilon result here. Okay. So this also implies, based on that connection, that it's unlikely that that question to John Rife is true. Actually, if you can do this in polynomial time, the original one actually is already in randomized polynomial time. Okay. So it's different from linear program. So this is not another version of linear program. Okay. So the complexity assumption is basically this PPAD, which I will give you an example. I will be concrete on this. Okay. So, but before I say anything technical, let me give the context of the result. Right? This particular result is not there for its own purpose. It's really the outcome of a sequence of development in our field. So we build a lot on the intuition of the people who work on this problem for many years. And here's a few results that influenced this particular one, and also a few of those whose technical advance that we build upon. Okay. So, for example, in 03, Lipton-Markakis method proved a beautiful result, even though it's a very simple argument, that an epsilon approximate Nash equilibria can be found in time almost approximate polynomial, but with epsilon on the exponent. There's a log n floating there. So this is the subject of a lot of current work right now. Okay. And So in 2004, Savani and Van Stingel from England proved that Lemke-Hausen take exponential time in the worst case. So this is not a very surprising result because the simplex method also in the worst case take exponential time. But it's a beautiful construction. It's beautifully reveal the structure of the polytopes. It's beautiful, elegant construction.
So the first one, to sort of understand how good or bad that is, what would that mean for the first log n bits or something?
No, you mean nothing. It has 0 consequence on log n bits. Yeah. In fact, you can't even get out 1 bit in polynomial time.
Quasi-bits.
Yeah. So you have to yank up your time to n to log n.
Because n to log n sounds.
Yeah, because n to log n will just remove. You can't even get 1 bit out. Yeah. And so then there's a promising news from 2005, which that's why I spend most of the time thinking positively, not thinking negatively. There's a nice result by Barani, Vampella, and Vetter from, I think they were all at MIT at that time. They show a randomized bimatrix games in P. By randomized, one particular example is A and B are Gaussian matrix, or randomly chosen from -1 to +1, randomly chosen. Then they show that such game can be solved in expected polynomial time. In fact, their scheme is very simple. They show that if you just observe 2 by 2 subgames, if you take that equilibrium with high probability, that's equilibrium of the whole thing. So that's but the proof is complicated. But the virtue of the story is basically if you just take a 2 by 2 or 3 by 3, solve those constant game multiple times, and one of them will be the equilibrium for the global one. Okay. So this is a sort of high time, which I strongly believe that the smooth polynomial time for bimatrix game is true, right? So I getting around shortly before this time and spend a lot of time trying to understand Lemke-Hausen at that time. And so then there's a breakthrough complexity development about the games, which eventually lead us to the result of approximation. So first, from Berkeley, there's a beautiful and breakthrough construction from Daskalakis, Goldberg, and Papadimitriou. So they prove that the 4-penguin game, the equilibrium for 4 players, is PPAD complete. Mind you, I haven't defined PPAD. Just take it as a hard class. I would, for sure, at least give you a concrete instance of that. And in two separated work with slightly different arguments, my collaborators and also Daskalakis, Papadimitriou, they're able to refine the argument and to prove that 3 monkey game is also hard. Okay. And but still at this stage, the popular conjecture is still the 2-player games is in P. So somehow 2-player game is special. It's special for 2 purposes. One is most of the proof technique at that particular junction, they break down at 2. Because they reduce to graphical game, and when number of players is 2, then suddenly the degree collapse into a sort of degree 2, that graph theoretically, the original proof actually breaks down. And the other one is that for 2-player game, it's very special. That is, for any A and B, you always have so-called rational solutions. Namely, there's always a solution that can be expressed in rational numbers, A divided by B. A and B are integers. And hence, if you want to have an exact, you just need to compute n bits for 2 integers to do the division. But for 3-player games, it's known from Nash that there could be rational game has irrational solutions only. There's no rational solution. Which means in the term of computer science, you have to approximate, right? Because there's no way to write it down in polynomial size. So that's basically, and also Lemke-Hausen is kind of useful in practice. That's why people continue to believe maybe eventually the technique from linear programming and advanced will resolve the solution of this. Okay? But then my collaborator Chen then proved that it's not quite true. It's actually as hard as 3-monkey game. The 2-player game is also hard. Okay. So in this context, built upon a lot of technique here, we took one step further, essentially to show the approximation is hard for fully polynomial time, and also hard for smooth complexity. So that's basically the global context of this.
So one of them is theorem and the other is quasi. What does unlikely mean?
Under condition of PPAD is not in P.
Oh, I see.
Right. It's under this complexity assumption. I will skip this. Right. So could be interesting to game theory. So actually, all those things are very strongly related with the exchange economies. And I have expert here, so I'm doing a very simple versions. If I didn't see precisely as in your mind, forgive me here. So here is a simple scenario of exchange economy. That is, you have a collection of traders, and each trader has an initial endowment of collection of goods. For example, if I just came back from China, I may have DVD. These days, nobody carries DVD around anymore. And what if I came back from Cuba, assuming I go there, I come back with cigars, right? So those called the initial endowment. And each player also has its so-called utilities, right? For example, I don't smoke cigar. Cigar really worth zero to me. But if you love cigar, I'm happy to sell you for $200 per stick, right?
I think that's illegal in this country.
Well, that's called exchange economy. There's no money exchanged. No money at hand at all, I promise you.
So are we allowed to do exchange?
Barter?
I think if we don't have money involved, we only borrow from spending dollars, right?
For bartering too, but let's not worry
So-
about it.
So essentially in this scenario, everybody coming with their initial endowment, they have their own objective functions. Clearly, everybody wants to collect as much as for their own objective functions. Then is create a trade, and then basically say, how much pound of grape you can change it for one stick of cigar, right? So essentially, it will create a trade. So how do we decide, who worth what in this ratio? So here is a so-called general equilibrium theorem developed eventually by Arrow and De Bruyne. So here is basically their scenario. They said, well, imagine someone fixed the price. Imagine, just first, don't worry about how the price comes yet. Imagine someone fixed the price. So let's consider the following distributed exchange. Right? So it's just like computer science, right? Distributed computing. So let's consider the following distributed exchange. Each trader just sell its endowment to the market. You know who is buying what. I came back from Cuba. I just sell my cigar virtually. I just virtually sell my cigar, and I get a budget. So this is dot product of my endowment with the price. I got my money. But money means nothing, and it's illegal for a cigar. So then I want to go to the market to optimize my utility. So what is the market? That's union of goods. I don't care who is selling. Just like I'm not caring who is buying, who is selling. I'm just deal with this virtual market. To the virtual market, it's a union of goods, and I'm just selling my fraction to get a budget. And then I optimize here. So they prove that under some basic assumptions, which I'm not going to get into detail, that the market clearing price actually exists. So by market clearing price, it means that a price vector that after this particular exchange, there's nothing left on the market. And nobody has money anymore. So that's why money is only intermediate stories. And basically, so the informal argument is that if there's still grapes left on the market, when nobody has money, the grape was zero. So probably the grape price was set up to be too high. And if somebody still has money in the pocket with nothing on the market to buy, like when I was a kid in China, actually we have neither money or good on the market, and then basically the money was nothing, right? So which means something is set up too cheap, right? So essentially, market clearing price is the one which allows you to do this completely in this distributed fashion. And they prove that on the reasonable assumption of utility functions, for any endowment, such thing exists. And clearly, the problem is how quickly we can compute. Okay, so here is basically a theorem, basically saying that individually you optimize, you have market clearing condition, and it's not a quasi-equilibrium. Namely, if you have no money, you're not allowed to buy anything. So that's the mathematical formulation of the equilibrium. Okay. So here again, there's a tale of two economies. Just like in the game theory, I mentioned two stories, right? The zero-sum game for 2 players and general 2-player games. They somehow behave differently. So here also there's 2 stories. So on one set of stories, for example, if the utility function is linear, and the other one is that the utility is so-called bottleneck, right? So linear utility is that suppose you buy a TV and VCR. So what is your utility? You just the value of TV plus VCR. And in the Leontief so-called bottleneck economy, if you buy a great TV, a louder VCR, when you project, you can only see a little bit picture on this great TV. Then your utility is just this louder VCR, right? If you get a fancy VCR with a horrible TV, your utility is this horrible TV. So this basically is set up when they set up factories, right? There's different components in the factory. In the pipeline, your utility is just the bottleneck of the system. Okay, so let's consider this 2 style of economy. And so on one side, we have a really local expert here. I'm not going to say too much. It's all implied that if it's linear exchange, it can be solved in polynomial time. There's many different ways to solve using approximation, using combinatorial approach, using interior point method. But the real story is that the solution space is convex, right? I think that's punchline, right? Yeah. The solution space is convex. So ultimately, all those solutions, eventually you all build upon this key fact, right? So it can be solved in polynomial time. On the other hand, so we are able to show that build upon an early reduction by Yin from Stanford and the joint work with Kondonotti, Saberi, and Jarin. So we are able to show, and also the 3-player game, we're able to show that for Leontief market, it's also hard to approximate. And it's also unlikely it's in smooth polynomial time. So again, in this market equilibrium, it behaves very similar to the game case. There's something similar to convex linear programming, there's something different. Okay.
What if you place a min by max?
Pardon me?
What if you place
That's the same thing if you flip the utilities, right?
Or because that could be negative.
So let me, using the rest of time, I will quickly go over some of the technicals. Right? So in the rest of time, I would like to mention a little bit of mathematics surrounding.
Equilibrium may not exist if you
it may not exist. Yeah. Depend on the right. Depend on the, so it's no longer this. Right. It's not concave, quasi-concave anymore. Right. So sorry. Yeah. So I would like to mention a few things which are fundamental, things that connect with equilibrium and fixed points. And one fun part is related with combinatorics and topology. And for us, it's basically what is different between existing proof and algorithmic proof, and what is different between mathematical theorem and algorithm. So it's beautifully showed up in those problems. So let me give a very quick tour of this. And it will involving a lot of brilliant work from brilliant people, from Brouwer, Spurner, Nash, and Crystal. Yeah. So here is one lemma which I really like, and it's a beautiful lemma connect between continuous math and combinatorics. Okay, so it's something called Spurner's lemma. Perhaps the easiest one to describe is one-dimensional. So imagine you have a line, an interval, and you color one end with red and one end with blue, And suppose you divide the interval into subintervals. You color anything in the middle arbitrarily. So then we know there must be a interval that has two colors at the end. So this actually is a combinatorial way to say about continuity. So it's basically equivalent to the theorem which we used to learn from high school or elementary school or college, depending on the country you come from. So namely, if you have continuous function, fa is negative and fb is positive, then there must be a root equal to 0. Right? So that's basically, and this is exactly that statement. If you have red is negative, blue is positive, if you sample, there must be somewhere you cross 0. Okay, so this is related to that. So Spurner showed that this thing is true basically in 2 dimensions and any dimensions eventually. That is, in 2 dimensions, suppose you have a triangulation of a triangle or any convex shape, doesn't matter. Suppose you color one end with red, one end with green, one end with blue. You color the side based on one-dimensional rule. Namely, this side you can only do red and green because that's a one-dimensional case, and this is a one-dimensional case. This is one-dimensional case. Then color interior arbitrarily. So then Spurner is able to prove that there must be a fundamental triangle that has all 3 colors. So his proof is topological. He actually argued the number of such triangles is an odd number. Since 0 is even, there must be have 1. Right? So that's how it's proved. Actually, this can be all done in 5 sentences. So I will skip that. And so this little theorem is very powerful. It actually allows you to prove Brouwer's fixed point. If you just do a finite difference against Brouwer's statement, that the continuous map from a triangle back to itself, or a convex set back to itself, always have a fixed point, namely fx equal to x. You can just do a sort of finite discretization, apply Spurner lemma, and take limits. So that's allow you to prove Brouwer's, and eventually allow you to prove Nash equilibrium. Okay. So a brilliant step Christo Papadimitriou took is that he examined the Lemke-Hausen and Orrell's argument. He defined a generic computational class called PPAD. And eventually, Orrell's result completed the cycle, saying that they are computational equivalent. So this is one thing I will give you a quick introduction. Okay. So how do we define computational class about the fixed point? You have to think big and think exponentially. That's all you need to do, right? So imagine you have a triangle. You divide it into small triangles by putting an exponential number of breaking points at every side. Right? So this is exponential space. And then suppose I give you a polynomial size circuit. So this circuit will take a coordinate and return a color. Right? So your input is just the circuit. You take coordinates and return a color.
Wait, but the input is exponentially not.
No, it's just a circuit. It's polynomial. This is just virtually defined. Because every coordinate is polynomial large.
So wait, you have
Every point is binary, right?
Exponentially many points.
Yeah, it's polynomial size. Because the number of bits is you have to take a log. Right? So the circuit is polynomial size. So you have this polynomial size, take a coordinate and a color, and so this basically is called computational version of Spurner lemma. And so this problem is a complete problem of PPAD. Okay, so just like I'm defining NP without telling you what NP is, I just say, think about 3 sets. So this is your 3 set for this class. Okay, so I will skip the definition of PPAD. Just give you a concrete example. So here is another concrete example defined by Daskalakis, Goldberg, and Papadimitriou, which is very similar to the other one. It's slightly easier to handle, but it's virtually the same. That imagine you have a square. On one side you color red, one side you color green, the other 2 sides you color blue. Interior you color any way you like. Then one can also show that for such coloring, there must be a square that has all 3 colors. In particular, there must be a triangle that has all 3 colors. Okay? In particular. So this, let me call it discrete Brouwer's fixed point. And again, this you can build upon computational problem. You can think about virtually and exponentially large space with exponential number of points. And you have polynomial size circuit to give you the color, right? Because you take a log of the magnitude. So, so for 3-dimensional, that's color kit Goldberg and Papadimitriou define. For 3-dimensional, they're able to show this is PPAD complete. So my collaborator, a few years later, is able to show even for 2-dimension is PPAD complete. So here actually they need a small trick here, namely in 3-dimension you can build freeways crossing each other. In 2D it's all planar graph, so you have to deal with the intersections. So they find a very clever way to handle the intersections to show this 2-dimensional is PPAD hard. Okay, so again, think large and exponential. You get your computational class. So this is another example of completeness. So here is this framework set up by Daskalakis, Goldberg, and Papadimitriou to prove game is PPAD complete. So the first step was they show is a very beautiful geometric lemma. And so imagine that you have this grid colored. And imagine you interpolate the color. You interpolate the color all the way continuously. Namely, you take a nearest neighbor, you just color that way. When you have tie, just ignore it. That's small events. We can just ignore that. Okay? And so what they argue is following. Beautiful lemma. That is, suppose you have any point in the space, and you look at a small, even smaller grid you build for it. Say 41 by 41. That's their choice. 41 by 41 grid with a small parameter k. Now they say, let's interpolate the color, and let's give a color a vector name. For example, if you see red, I go in with 1 over k as a vector. If you see green, I go up 1 over k with a second exponent. If you blue, I go diagonally in with both sides. So if you really think about this, this means that this direction you go in, this direction you go in, the other direction you go diagonally in. You must have a fixed point. There's no way to escape. Somewhere you have to stay on yourself. So that's essentially the argument. And so they're able to prove the following lemma. That is, you add up the vector you sampled around the points. If they happen to be very close to 0, say exponentially close to 0, then this square must have all 3 colors. So the reason is very simple, right? Because one vector has exponent in the first one vector has exponent in the second one, the other one is 0. And if you miss the third one, there's no way, no cancellation is done. And hence you cannot go to 0. The only way to cancel is you have all 3 colors. Right? So it's a very fundamental observation here, right? You need all 3 colors to have a cancellation. So built upon this beautiful geometric lemma, they're able to move on for a framework of reduction. So essentially, they said, suppose I have this coloring circuit, they're able to build a 2-player games. And if you're able to compute a very, very precise equilibrium, namely exponentially precise. So they initially built for 3-player games. So eventually, this all reduced to 2 players, right? So initially, they did 4 players, but the same philosophy eventually, a scheme went through. Namely, you have coloring, 3-dimensional coloring or 2-dimensional coloring. You can build a game, either 2, 3, or 4, 5, 6, doesn't matter. And then if you compute exponentially precise equilibrium, you're able to pull back to find a 3-colored triangle. Okay, so this is a flow of the reduction. Okay, so I will skip the detail. I just want to point out one thing about approximation. This reduction is insufficient to prove the approximation results. The fundamental reason it's insufficient to prove approximation result is that here they need exponential precision to have this happen. And in order to prove the approximation result, we need to argue if you get a polynomial precise approximation, you're able to pull back. And I can give you a simple argument. In this original argument, it will not go through. So here is a simple reasons. Why they need to set up epsilon to be exponential. Because the point space is 2 to the n by 2 to the n. In order to tell you where you are in the space, you need n bits. And if your equilibrium is not precise enough. You don't even know where you are in the space, let alone to decide whether you have enough colors or not, right? So this is why they have to use exponential precisions. So for us, in order to prove this approximation result, we need to show an approximate equilibrium is able to pull back. And hence, you have to change the reduction or change the sort of potential space of reduction, right? So this is one of the technical difficulty in the past. So let me briefly show how these steps are done, then I will conclude the talk. So here is a few things which we learned from our heydays of parallel computation, right? So that is, remember when we first built a machine, we built a mainframe, a single machine. Then people began to build parallel machines. The first parallel machine they built is a few processes connecting a line. And then people say, well, technology become more fancy, let's build parallel machine this way. Then eventually someone say, well, let's build three-dimensional parallel machines, right? So that they communicate with their neighbors. So eventually they build a Hypercube with thinking machine cooperation, right? So you can see the connectivity actually went to a higher dimension. But those are just the so-called grid graph in different dimensions, right? And Hypercube is just a cell, right, in any dimension. So I would like to go through this one, and it's related with parallel computation. So if you look at Hypercube, those are the fundamental units in every dimension. So in 3D, it looks like this. And in 8th dimension or 9, it looks like this. But virtually in our mind, it's very simple, right? It's just a cube, right? So the beauty of high dimension is the following. You can trade precisions with dimensions. So let me argue the following one. So you can talk about high dimensional fixed points. That is, the difficulty of fixed point search came from the searching space is exponential. Right? If the searching space is polynomial, you just examine it, asking for every color. So the only thing is hard potentially is exponential space. And this was normally we say, you find a needle in a haystack, right? So you have to have enough space so that the needle is hard to find. If your space is small, you will find the needle, right? So you have to build exponentially. And if you go to higher dimension, you can actually reduce the side length to have the same volume. For example, in 2 dimensions, suppose you want to hit a volume 2 to the 2n. You need 2 to the n by 2 to the n. Right? But if you go to 2 to the n over 3 dimensions, you only need 8 by 8 by 8 by 8 grid to build enough volume. Right? Because you have so much dimensions. So suddenly, your precision becomes 3 bits. With 3 bits, you know where you are at every component. The other one, you need to ask n bits to know where you are in the space. Right? So essentially, one of the observations we're able to show is that the fixed point, the extension of a 3-dimensional fixed point to n dimension, which means you use n plus 1 colors, is also PPAD hard in this very compact space. And therefore, we're able to handle all the things in 3 bits. And therefore, we're able to show the approximation result. So that's basically the sort of outline of the this approximation reduction. Okay. So let me quickly argue this. Find the panchromatic simplex. Panchromatic means all colors. I learned from my GRE. In hypergrid of 8 by 8 by 8 to the n is PPAD complete. So that is I have an n-dimensional hypergrid. One facet I color 1 facet 2. You have n principal facets. Then all other facets you color n plus 1. And then interior you color any way you like. And the hard part here is that you cannot say a cube. A hypercube has all colors because a hypercube has 2 to n nodes. So you have to say simplex living in a hypercube has n plus 1 colors. So you can see there's certain refinement one has to do. There's a technical difficulty in handling all those steps, but nevertheless, eventually can be done. So we are able to show this is PPAD complete. So let me give you a quick argument. So here is, again, during the heydays of parallel computation, that is when people began to write parallel program for 1 dimension, at least in CMU, when H.T. Kong's group built the 2D grid, then his group said, how do we run our parallel machine? We already write so many programs for the 2 years. The first answer is that why don't we embed 1 dimension to 2 dimension? So at least our program is still running there with less efficiency, but it's running there, right? So you can see 1-dimensional, you can snake it into 2 dimension. But again, the side length already takes square root in the same volume, right? So let me give you a 1D to 2D reduction. I trust that once you see 1D to 2D reduction, you will get into any dimension, okay? So in 1 dimension, suppose I have a Splinter problem, as I show, then I can embed them into 2D like this. For technical reasons, we have to skip every row, and I have to withdraw a little bit. So in order to create a 2D instance, I color the boundary accordingly. There's no choice to do that. And then we properly fill in the middle. Okay? So then, in this configuration, you can argue, every time you have a trichromatic triangle, you're able to go back to the 2-colored interval. Okay? For example, this particular one, we go back to 2-colored interval. And this particular one, we go to 2-colored interval. You know, they can switch the position, but it doesn't matter. Every time you have 3-colored here, you will get 2-colored there. You have this one, you will go back to here.
Oh, that's because you left out exactly one which you have monochromatic.
Yeah, then you need to systematically do this, right? So there's 2 types of proof that I learned since I become a computer science student. One is called zero knowledge proof. The other one is proof by example. So I hope I gave you a proof by example which is less zero knowledge to you. Okay, so this is my proof. Okay, it can be done systematically. You can do this way. Okay, and then with induction, you can prove the whole thing, right? So you can continue to fold. So you started with this exponentially large sheet, right, of 2 to the n by 2 to the n. Then you continue to fold it, and eventually you fold them into 8 by 8 by 8 grid continuously. So you just continue to do this folding. And eventually
Go from 2 to 3 dimensions. Do you just
you just do 1 dimension, yeah. So each time you just pretend you just only get one dimension, yeah. Right. You continue to fold this way. So so once you can, so inductively you can prove that if you fold eventually enough to 10n dimension, you're able to fold this thing completely inside there. And then when you have a panchromatic simplex, you're able to withdraw a trichromatic triangle. And this is all polynomial relationship. Okay? So this proves that as long as you have enough volume in high dimension, it's hard. So there's another problem which we need to overcome, which I'm not going to say too much, but it's technically involved. That is
triangle should you? I mean, your example from 2 to 1 was triangle to edge.
interval. Yeah.
So shouldn't it be from a panchromatic simplex to an interval?
No. I stop at 2 dimension. I don't go to 1 dimension. Yeah, because I started at 2 here.
Right. He started with.
Yeah, I just show you a toy example to show. Yeah, this proof. The proof by example, right? So I show you that one, and I say, okay, if you believe that, you actually can prove everything else.
You gave us a proof of irrelevant result.
I can tell you proof totally irrelevant, but it's totally relevant because everything just built upon that wrapping. Yeah. So that's one of the basic transformation you need to do, called snaking. Yeah. Right. So, but I didn't go all the way to 1 dimension. So I go to 2 dimension. So there's one thing which is always tricky when you play with high-dimensional geometry. The high-dimensional geometry, the difficulty is the curse of dimensionality. Just count how many corners are there in a hypercube. That is exponential. So that's why you have to alter your definition all properly, right? So for example, remember this sampling lemma of Daskalakis, Goldberg, and Papadimitriou for this 2-dimensional case. That's the starting place of reduction. So they prove that if you sample 41 by 41, eventually you are able to do this thing. But if you straightforwardly using the idea to high dimension, then you have to sample 41 by 41 by 41. then it's becoming exponential. You can't use those things to do the reduction. So this is called the curse of dimensionality. And fortunately, we're able to reduce that into polynomial size, the sampling. And so one had to show that the certain style sampling, if it's close to 0, then you're able to find a simplex you can find a simplex that has all colors, right? So it's not a cube. You have to find a simplex that has color. All those things has to be done in polynomial time. But let me just skip that. So essentially, with this reduction, that's essentially all the part of contribution I was involved. Namely, once we can build this high dimensional one, we can just build upon the existing reduction scheme to push it into two-player games. Okay, so that's how the approximation is proved. Okay. So let me quickly wrap it up. There are a few extensions one can do. For example, we can show sparse game is also hard. If you have a game that most of the rows and columns are zeros, you have 10 non-zeros everywhere in every row and column, that is already hard to approximate. Okay. So the other hard to approximate, this joint work with Paul Valiant, is that if you have win-loss game, like when you play baseball, if one day, Red Sox beat Mariner or vice versa, 17-1, it's still 1-0 game. It's still, you just win and loss, right? So in such a game, we also be able to show find the approximation is hard. So in some sense, you don't need much in the game. Suddenly it's become difficult. And so there are quite a few open questions which I think it would be interesting to resolve. The first one clearly is the one, do we have a polynomial time approximation scheme? If you're allowed to put 1 over epsilon to the exponents. I don't know the answer, so I'm working on that too, but I don't have a too good idea right now. Okay. And the other is what would be the natural condition for easy game and the market? There's a famous quote from Kamal, people always cite, which I'm not going to repeat since he's here. So fundamentally, in practice, we often say something are easy, because otherwise, why we use it, right? So for example, partially we went through a smooth analysis. Is to find some fundamental reasons in practice is easy, and as weak as possible, right? So in smooth analysis, we basically try to say, well, if you have enough imprecision, then linear program can be solved fast by simplex method, right? So here basically the imprecision is not sufficient for two-player games. Then what other sort of practical conditions make it easy? So whether two-player games is important in practice, right? So I'm open to debate on those things. And but I think probably there could be some very beautiful mathematical theorem too to find the sort of right conditions that sort of meet partially the practical concern and theoretical concern. So I don't know right now. And the other question, beautiful question, is how hard is PPAD? And the first time I mentioned the result to Andy Young, then he basically said, I'm not so sure how hard is PPAD. Like NP complete, there's so many people thought about it. PPAD, at that time, only Crystal thought about it. But I said, Crystal is a smart guy. If you look at all the reduction he can do, so the PPAD could be hard, and it also could be in polynomial time.
How hard is PPAD? How smart is Crystal? I don't know.
Crystal is smart. Crystal is smart.
He reduced one to the other. I mean,
Papa Dimension, right? Yeah. Papa Dimension. So it's possible that all those things could be in P, but I think it's hopefully we can find other mounting evidence to show it's not. Right? So to relate it with some other classical result. And I have a few results with my collaborators with
Wouldn't it be better if you were wrong? Why do you say hopefully?
Yeah, wouldn't it? For the market.
Well, in the theoretical result you can interpret in any directions, right? So, for example, factorization is in polynomial time. It could be good news or bad news, right? So
Is it totally unrelated to factorization?
That's one of the questions. For example, one of my conjectures is try to relate one-way function. If one-way function exists, can we show this hard? So there's different conjectures I would like to put out, but I don't know what is true. I think many other people ask similar questions. It's not just myself. I'm sure Crystal has even more advanced question, which probably closer to be true than what I can put up right now. Yeah. So how hard is PPA? I think it's a beautiful question. In some framework, for example, in Oracle model, I gave a talk last time, so I'm not going to repeat that. Some evidence it may not be that easy. One has to have sufficient breakthrough to solve this. Yeah. So let me end with one thing. That is, when I began to give this talk, people ask me, where do you work? Are you working in game theory or economics, or you're just a theoretician? So I said, I'm just a theoretician. I really, I'm interested in economics problem, but I'm a theoretician. Then they said, well, then you shouldn't claim you're working on economics problem. So I think hard. Then I was talking to my student, Kyle Burke, at BU. I said, people always criticizing me that I have this economics result. They said that you're not really working there. It's just a bunch of theory. I said, I really want to have something related with economics, and also the thing which I studied. So Kyle basically came back with a brilliant idea. He said, you're talking about economics, internet, and game. So I can give you one thing that has nothing to do with traditional economics, but potentially related with economics. Okay, sort of
And you can call it game theory.
humorous way. So this is just a humor now. So he said, let's define a game based on Splinter Slammer, which is a brilliant idea. So he said, let's define a recreational game. Let's put it online. Let's trademark it, and hopefully people buy. That's economics. You put online, that's internet, and you're using all the equilibrium and fixed point. That's game theory. So that's basically one of the following results, which it turned out to be really cool. So he defined a game as the following. You have this is a game board, and it can be parameterized in the size you want. And you color the boundary with alternating color. Right, so you can see this is just one of the boundary conditions of Splinter Slammer. You leave the intermediate empty.
You're cheating. It's not
Yeah, there's blue there.
No, every side. So this is the other side. Yeah. Okay. So you have a canonical way to color the boundary according to Splinter. It's valid Splinter coloring. And then the game has the following rule. Players take turns to color the circles with one of the three colors at every step. And the player who creates a three-colored triangle will lose the game. Okay? And if possible, so this is a special rule. There's a different rule, but this particular rule we have is that if possible, a player must play in the adjacent circle next to the one which is previously colored. Okay? So this game is simple, right? So then we said, what is an interesting game? So then you go to think about what are the interesting games. Interesting game has to easy to build, simple to define. Hopefully, it's inevitable someone will win and lose, right?
I don't understand what you mean by it's not possible.
If it's possible. For example, if I color here, if everything here is colored, you are free to move in any other place. Otherwise, you have to.
But there's the next. I mean, what do you mean by?
So you suppose this is the last color, and those six are its neighbor. If one of them is uncolored, you can only choose that color.
But now, once these are colored, then this guy has neighbors.
Then you're allowed to jump.
Then you're allowed to jump.
But
Yeah, that's the rule.
But I don't understand the rules. So
Okay.
what is the rules? Because everybody always has a neighbor. So
Yeah, but some neighbor are colored.
Not
Yeah.
if you, think about it, it's once you complete a
You-
loop and you go inside then.
Yeah.
Then you don't have
Then
any.
you're
Then you don't have neighbor anymore.
disconnected from
Yeah.
the rest
You
of
need
the,
uncolored
from the,
neighbor.
then you're no longer in the connected component of the rest
Now
of
you
it
can jump.
now. And now you jump.
So clearly a simple rule is just you can choose an uncolored one, color it. And this one is you choose an uncolored one, color it.
More interesting with this Addition.
So I can show you a few things. Yeah, I can show you some conjectures there. So that's why the
There's nothing adjacent to it. It's not very colorful.
Because you did
yeah, because right.
Because
Right.
you did the
So that's the rule,
function.
right? So what's an interesting game? If you look at all the interesting games like chess, the Chinese has this Go, right? And Nash invented the hacks, right? It's different games.
Did Nash invent it?
Yeah. So why is it interesting? They have simple rules. Well, I'm not sure about chess, but they have simple rules. And it's difficult to play, right? So what is meaning of difficult to play? In modern days, it means that it's very hard to write a computer program to beat a human. So imagine that a computer program can, in polynomial time, always decide win or lose. Then there's no chance for a human to play against the computer. Right? The computer just, in short time, let's say in n squared time decided. And it's very hard for a human to do that task. Then we always lose, right? So, so if you look at all the interesting game I mentioned, chess, Go, they all basically say find winning strategies piece-space complete if you parameterize the board. The hacks is NP piece-space complete to play. The Go is piece-space complete to play. I think hacks read out due to Tarjun and many other people. And the Go read out due to Max Sipser. And Crystal has multiple readout about piece-space complete games. And so we are able to show this game is also piece-space hard to play, right? So not only that, this game is interesting is because it's not a monotonic game. So if you look at hacks, so especially here, people see the hacks of Dave Wilson, right? So this random hacks. And in hacks, basically, it's a monotonic game. Namely, at any junction, if I ask Jennifer, would you like to skip your move? You say, go to hell, I'm going to move. Even a bad move is a good move, right? Because if you don't move, it's monotonically losing. But here it's parity game. Right? It's parity game. The winning or loss are in the parities. So if you can decide moving is bad for you, you should skip. So it's not a monotonic game.
You patented it?
So we have trademark of this. We have to, and my student began to build a board for this, different design of this. And to come back to your question, if we remove this part of the rule, I think we still conjecture that's in polynomial time. We have some evidence it's in polynomial time. So it could be interesting result, but we haven't been able to seal the deal right now. Okay. So so this is my little adventure in the field of game theory, economics, and internet. Thanks, yeah.